Good afternoon and welcome to this week's Iowa Learning Farm Conservation webinar. I'm Matt Helmers. Glad to be back from the Eastern Shore of Maryland to be able to moderate the webinar today. And so this week we're able to welcome Dr. Sotirios Archontoulis, that's an associate professor in the Department of Agronomy at Iowa State University. Dr. Archontoulis does a lot of work as a world-renowned leader in the use of the APSIM model, teaches a APSIM modeling workshop, I think most years, and I think it's coming up in June of 2023, if I'm not mistaken. So if you're so taken by the work that he's done and want to learn more about APSIM modeling, there might still be opportunities to get in, although I know it fills up quickly. But with that, Dr. Archontoulis is going to talk to us today about the review of Iowa water and nitrogen balances using the APSIM model. And if you, as always, if you have questions for him, please type those into the chat box and we will get those to him at the end of his talk. And with that, Sotirios, the virtual floor is all yours.
Matt, thanks for the invitation and the opportunity to present today. I really appreciate that. And the work that I'm going to present today is going to be heavily based on modeling results, and in part is supported by the Iowa Nutrient Reduction Center. Two motivations behind this work that we're going to see review together in the next 20-25 minutes. I do provide some reviews of crop aspects, crop yields, what happened in the previous years, and I wanted to keep a balance between the crops and the soil aspects, including the water and the nitrogen. So going after a systems understanding what is going on. And most important, found that examining what happened in the past, the temporal changes, can greatly inform us about some future management strategies to pursue with the climate change. So today we are going to talk about the nitrogen and the water balances. And I will start with the definition. I have seen many different ways of defining water and nitrogen balances, and I will start with that to be clear up front. In terms of the water, we always have a starting moisture at planting, at first day of the year, at some short of time. Once we have this soil moisture, then we have the inputs, which are mostly the precipitation and irrigation, although we don't have much irrigation in Iowa. And then we have the loss of the water, which can be through the surface runoff, drainage, either tile drainage or deep drainage, soil water evaporation, and transpiration. And after all these processes take place, the soil moisture is going to be at a different state, let's say at harvest. So we will deal with all these processes in my presentation in the way that did the water balance. And I should include also there the contribution of the water table. I'm going to say a few things later on. Nitrogen is similar format like the water. We have a starting point in organic nitrogen, and then we have the inputs from the fertilizer and also the contribution of soil organic matter mineralization. Then we have some immobilization from crop residues, not all of the times. Sometimes we can have mineralization of crop residues, so we can put a plus sign there, but most of the times it's a negative sign. Then we have nitrogen leaching to waterways, denitrifications and denitrification, NTO and NTO, and of course, crop N uptake, which is a large flux, a large amount of nitrogen that the plant is taking up. And then we have some sort of remaining nitrogen at harvest or at some other point. A second aspect to consider about balances is the spatial variability across the landscape and also the temporal changes. In Iowa, we don't have much diversity in terms of crops, which is good for crop modelers like me. So we don't have to simulate many different crops. With 2 crops, we have a good representation. But Iowa is quite unique in terms of soil variability. We have very high soil organic matter at the top, low at the bottom, so the delta is quite large. And also we have the spatial variability from east to west in soil carbon, plant available water, also water table depth. This is a huge deal for Iowa. And at the same time, we have the temporal changes in management and crop yields, which keep going up. There are some excellent reviews of nitrogen balances for Iowa. Mike Castellano, Matt Helmers, and other colleagues put together all the science experimental data we had by that time and created a beautiful document. I always read and refer to this document, and I put it there for your references. What I did in this study was to move a step forward to get this information from what we know about the balances in Iowa, integrate the environmental variability, soil and weather, genotypic variability, the genetic gain that we have observed over the last 30 years, and the changes in management, and create a systems perspective simulation, nitrogen and water balance for Iowa. About the model, thanks, Matt, for saying a few words about the workshop that we have every year. Yes, we are going to run it again. It's June 13 to 15 in Ames, Iowa, and registration is open. Whoever has interest, please email me and I will send the registration link. About the model, APSIM, Agricultural Production System Simulator. This is the name. It is a very advanced simulator of cropping systems designed to address genotype by environment by management interactions, has capabilities, and we prove that through lots of publications to model cover crops, tillage. It accounts for shallow water tables and tight drainage in the landscape, very flexible with the soil inputs by layer, comprehensive nitrogen and carbon cycling models. And we have done quite some improvements to simulate appropriately the crop roots and the excess moisture stress on crop yields. Several publications, with the most recent one to be the one that we published this month, actually, and it has to do with simulating long-term corn yield response to nitrogen in continuous and rotated crop system. Mitch Baum, my PhD student, lead this publication, and with the input from Sawyer, John Sawyer, Emerson Napsiger, Isaiah Huber, Peter Thorbull, Mike Castellano, and myself. And the workshop where we have lots of fun, and we can talk another time about this. Important, the APSIM model is a field-based model. It's a single point. And the way that we deal with spatial simulations is to have a framework where we can run APSIM in parallel. And this framework is called PSIMs. And as you see in the middle panel here, we have a paddock, and then by running it for many times, we can simulate the agricultural landscape. Importantly, we have to specify the inputs into the model. And then the model is going to give us the outputs. In terms of inputs, we work with daily precipitation, temperature, and radiation. We account for most soil information, changes in planting date and rate. We try to represent what maize breeding has done to the corn hybrids over years. And of course, we have to make some assumptions to make the whole system work. We have many data to prove that the model works well, or if not, we go back and change it. A very quickly overview of the inputs is very important in order to understand the outputs. Rainfall is increasing. Annual growing degree days over the last 40 years is increasing marginally, or no increase, I will call this one. Radiation, similar like thermal time. Nitrogen fertilizer input that we use into the model is increasing by about 0.7% per year. Plant density is increasing 1% per year. The blue points that I have there is from USDA NAS, and the planting date is getting earlier and earlier by about 0.1% per year. Account for many different soil aspects, including organic matter, texture, fraction of tile drainage in the landscape, the slope of the terrain, many different inputs. And let me show you some of the model outputs, the validation of the model before I go to the water balance. Here you see the state level, Iowa state level, simulated maize yield with the blue points and the observed from the NAS. The correlation between the two is 0.84, and I'm happy to see that the simulations are very close one to each other, and I'm more happy to see that the model captures the historical increase over the last 40 years. This is very important to approximate the water balances. We did the testing of the model not only at the state level, but for each specific county. And this is impressive what one of my students did. They put 100 panels in one figure. The yellow points are the measurements and the blue lines are what comes out of the model. So we are confident the model works well there. And we did additional tests with the flowering time, silking time, and also we check the simulation of the water table depth. On the left, you see the information we have from the sorghum. The darker the color, the shallower the water table, and the yellow is the color, the deepest the water table, more than 3 meters or so. And on the right, you see what comes out of the model. And this product, this map, is the average of the last 35 years. We have simulations for every year and every pixel that we simulated in Iowa. Now, water balance. Let's make a start. Historical trends in rain, evapotranspiration, drainage, and runoff. X-axis are the years, and now different colors represent different processes or inputs. Rain, as I mentioned before, is increasing 0.5% per year. Evapotranspiration, this is simulated evapotranspiration, has remained constant according to the model outputs. This is surprising. I will speak a little bit more about this later on. Drainage, this includes tile drainage and bottom drainage, is increasing by 1% per year, and this is mostly driven by the rain. And runoff, it was the process that increased the most. And I guess this is not a good result for soil erosion, because runoff is highly tied with the soil erosion. Rain is the main driver for many of these processes, and after doing some sort of data analysis, what we found as a general take-home messages is that above 21 inches of precipitation, 50% of the extra water is gonna go to drainage and 30% to runoff. Evapotranspiration with rainfall didn't have the linear relation that we have known from the literature, but it was kind of a flat line. And the reason for this is the existence of the water table. Rain is one source of water. Water table is another source of water that is not reflected on this panel. And this is what it calls the flat relation over there. Additional evidence that the evapotranspiration has remained constant over the years is some measurements that we took in the summer of 2022, where we installed neutron probes in field experiments with different hybrids, old hybrids and new hybrids, and we measure soil water. And there was no much difference in volumetric soil moisture and that was a 9-feet assessment. This is the total soil moisture between all the new hybrids, but we found quite some differences in yield. If we divide these two, the moisture and the yield, we calculate the water use efficiency, which is increasing over the years. The product of all these processes is the soil moisture. And for 2 time periods, May and August, on the left, I show you the relative soil moisture. The higher the value, the wetter the soil. And seems like there is a trend towards wetter soils, no matter if we measure it in May or August, although in May is much higher than in August, which makes sense. The water table depth, in contrary, is decreasing, and this means that it's getting shallower. And the main driver for both these state variables is the precipitation, is the increase in precipitation. I want to share some more results on the crop rooting depth, which is important. And we didn't find any trends over the years. When we regress the rooting depth with precipitation or water table depth, we notice that there is an optimum of around 32 inches of precipitation. This is when the root depth is maximized, and the maximum was about 60 inches. Keep in mind, these data are statewide averages. It integrates all the historical variability in the weather and also the spatial variability. On the same time, rooting depth was highly correlated with the depth of the water table. And in that case, the optimum water table depth to maximize rooting depth was about 90 inches depth in the soil profile. There are so many different drivers and effects on the rooting depth, which makes the system quite complicated. And this is the strong correlation between water table depth and precipitation. The higher the precipitation, the shallower the water table. This is what I want you to keep from that. And in terms of practical applications, we did a recent study using workable days observation surveys, USDA surveys data. And we basically model these observations using different approaches. But a message that I want to share with you is that the number of field days suitable for field work in central Iowa is decreasing by about 0.36 days per year. And the majority of this decrease is coming because of the decrease in days suitable for field work during spring. So this is not a good result, and this is something we need to think and create adaptation strategies. We need to be able to go faster and do all the field operations. Nitrogen. I'm going to switch gears now, and from water we will go to nitrogen inputs, outputs, and processes. On the left axis, we have kilograms nitrogen per hectare, which is, I will say, equivalent close, very close to pounds nitrogen per hectare. Apologize, I didn't change the units there. And let's start with the largest in terms of magnitude input and walk all the way down in terms of magnitude. Nitrogen fertilizer to the corn. That was an input to the model, and it was increasing by 0.7%. The grain export, what was simulated by the model, which is the combination of increasing yield and decreasing grain protein, which was factored into the model, was increasing by 0.9% per year. This is the orange line. Nitrogen mineralization across the 35-year period did not change. We did not see any trend of increasing or decreasing. In terms of the amount of nitrate that is left over at crop harvest, and I'm talking about 0 to 4 feet depth, that was decreasing by 0.7% per year. And the majority of this decrease was caused on what happened in the 4-5 years in the simulation. In the last, I will say 20 years, it was pretty stable. And going to nitrogen loss, which integrates denitrification and leaching, that was increasing by 0.8% per year. Again, this increase was driven by the climate, based on analysis we did. Another important aspect I want to share is the distribution, the partitioning of nitrogen loss between leaching and denitrification. When we ran the model, we were expecting leaching to be the majority of the nitrogen loss. However, the results we got, it was the other way around. And one main reason, after searching and making lots of diagnostics, why denitrification was a bit higher than leaching in terms of total and loss is the existence of the water table in Iowa. Once we take this off, leaching is by far the #1 nitrogen loss. But once we integrate the contribution of the water table, then the fluxes are changing. Nitrogen is going to change the way that it's going to escape the system. Nitrogen loss divided with grain yield. This is a common index. It's a yield. Is the efficiency of the system. It's a measure of the efficiency of the system. The scaled emissions or nitrogen loss is based on grain yield. And good news here is that we have 1% per year, less nitrogen loss per unit of grain yield. And these are the statewide simulated data set, the regression line. And I would like to indicate the coefficient of variation of this data set. It was enormous. It was 57%. And if we see the individual coefficient of variation of nitrogen loss, that was 47%. And in the grain yield, it was about half of that or even less. So the majority of the variability in this sort of data set is coming from the nitrogen loss, not in the variability in the crop yield. And if we want to see the main driver again, which is precipitation, the relation between yield and precipitation is curvilinear. It's a polynomial fit where yields are maximized around 1,000 millimeters of rain. But when it comes to nitrogen loss, it is an exponential fit. The more the precipitation, the more the amount of nitrogen that we are going to lose from the system, no matter the pathway. The improvements that I mentioned before, we can see that over time is getting better. Despite the increase in rain, the metrics of yield scaled nitrogen loss is getting better. And let me describe this left panel a little bit in more detail. The blue points in line is the relation between yield scaled nitrogen loss and precipitation. And the orange reflects what happened in the last decade. The blue is the first decade back in 80s, 90s, and the orange is from 2008 to 2019. What we see here is that for the same amount of precipitation, let's say 1,000 millimeters, we have a nitrogen, we have the yield scale emission at that point. But when we go to the historical weather data and practices, this is a combo altogether, it is even higher. So this is good news. Despite the increase in precipitation, we see improvements in terms of productivity and environmental sustainability, the way that I interpret this graph. And on the right, Again, I list the main driver, which is always the water and precipitation in this case, and the relationships with the grain yield. Much of this improvement is coming from the increase in yield, not in terms of nitrogen loss improvement per se. It is mostly coming from the yield improvement. And what I described before with the yield scale nitrogen loss, it holds for the state of Iowa, and also it holds for different regions within Iowa. On the left, you see Des Moines lobe data from the Des Moines lobe simulated data, and on the right from the Western Iowa. The Western Iowa doesn't have shallow water tables, so the magnitude is a bit less than on the left. Now, let me try to summarize everything here and to close that and bring it into a perspective and then open it for discussion. On the right, I created a summary table with all the variables that we went through in the previous slides, and I list one particular value there, the percent change per year. For the evapotranspiration, it was 0. It was not changed according to the model. Drainage was increasing, runoff was increasing even more, the water table depth is becoming shallower, the soil moisture at 0 to 3 feet depth is getting wetter, so we have more soil moisture. We didn't notice any trends in the rooting depth. We have about the same rooting depth, and this is 1.5 meter, 5 feet. That's about the water balance and some main processes. The next group of variables is about the nitrogen. The grain nitrogen export has been increased, and this increase is mostly driven from the grain yield increase. Nitrogen mineralization has not changed over the last 40 years, and the amount of nitrate at harvest is decreasing, which I believe is another positive message for environmental sustainability, because as we have less in the soil profile, the chances, the potential of this nitrate to be escaped from the system is less. Everything is driven with how much you have in the soil. Nitrogen loss over the last 35 years has been increased by 0.8% per year. Grain yield, the simulated yield, has increased 1.6, and that was very, very close, and we are super happy with that, with what has been reported by USDA NAS. Yield scale nitrogen losses increased by 1% per year, and crop biomass has increased as well. So this is important. It's not only the yields that are increasing, are also the total biomass and the amount of stover that we have to manage. And the amount of stover changes significantly both water and nitrogen balances. When it comes to water, it changes the soil water evaporation, the amount of water that is retained in the system, and overall drainage. And in case of the nitrogen balance, it has a strong influence on the immobilization of nitrate and ammonium from the soil profile. So increasing this amount of stover, something that we need to think more on how to best manage this. In summary, key findings: wetter. I don't think this is surprising to anyone that is getting wetter. Higher grain yields, improved nitrogen loss per yield, and more biomass and stover production. Besides the effects on evaporation and immobilization of nitrate, another positive outcome of this analysis, and what I see by the higher biomass, is that over the last years, through the changes in genetics, management, and environment, we are able, the same growing season, to capture more CO2 from the environment. Now, whether we store this into the soil, this is another discussion. And I will not get into that in this presentation. Another noticeable changes is the significant change in plant density. 1% per year is it's significant in my perspective. And according to what we have seen in the literature and we utilize in our modeling, nitrogen fertilizer has changed, has increased. And a recent study, which we are about to publish with my PhD student and co-authors, here you can see the picture of Mitch Baum, who did all this beautiful work. He found that the economic optimum nitrogen rate is also increasing for Iowa and Illinois. It's not only the inputs, but it's the optimum. The crops require more to maintain the yield levels or further increase the yield levels. This is a kind of a summary, big picture, everything in one slide of water, nitrogen, and crop aspects for Iowa corn-based systems using a modeling approach, the APSIM model. And as we think about the future, this is my concluding slide. I want to leave it up there. First, now we have to think for the future. How can we change, improve our management practices in order to further increase production and environmental sustainability? And main driver for any decision we are going to make is the weather, and in particular the precipitation, which I mentioned quite often in my previous slides. That is the main driver for pretty much all water processes and nitrogen processes, everything in link to precipitation. Here is some data from one model and one emission scenario. We have way more, and we're looking and thinking about what is coming. But what I wanted to tell you here is that the variability as we move on the right is significantly increasing from year to year. We have years with 300 millimeters of annual precipitation, and the next year we have 600, so we have double number. But as we look at the historical data, the variability, especially in the very early years, was much larger compared to what the climate models are predicting for the future. This is going to be quite challenging, and we need to think more about the interannual variability and how we make our cropping systems more resilient. And with that, I will finish my presentation, and I will open it up for questions and discussions. And again, I want to thank Iowa Nutrient Research Center for funding support, FAR, and many other institutions for funding portions of this study. Of course, my research group for working and generated lots of great images and results for me to present. Collaborators, Mike Castellano, Matt Helmers, we had tons of discussions about modeling results and many more to come. Thank you, and I will turn it back to Matt to, I don't know, it's time for this slide now?
Yes, we'll go through the next quick slides, and Sotirios can take a drink of water if he needs it, and we'll get ready for questions. So if you have some, get them in. But first off, if you are watching and need a CCA CEU, please send your name, the name you entered to watch the webinar, and your CCA number to Elena Whitaker, ALENAW @iastate.edu by 5 o'clock today. Again, ALENAW @iastate.edu. Maybe we can go to the next slide, Sotirios. And if you watch this webinar live and are willing to fill out a voluntary demographics survey, you can go to iowalearningfarms.org/survey, or you can scan that QR code. If you're quick, we'll leave it there for 1 second. If you've done this for a 2023 webinar, you don't need to do it again, but if you're willing to do it, we'd certainly appreciate that. This is voluntary, but because of our participation in USDA-funded programs, we're asking for this. And then a little plug for the webinar next week, and that will be me. So I'm going to talk about some of our work looking at cover crops on nitrate loss. So tune in then, won't put any more plug in than that. Okay, there are some questions that have come in, Sotirios. And the first one is, can this model potentially be used to make field level economic optimum nitrogen rate recommendations?
In theory, yes. Yes, it can be used, and some different models in the past has been used for this type of approach. So the answer is yes. To elaborate a little bit more on that one, it is critically important to ensure that the inputs into the model are as accurate as possible. It is extremely important.
Another one was the relationship between water table depth and precipitation would be different for drained versus undrained land, right?
This is absolutely correct. And also, even within drain fields, we're going to see different magnitudes because of the different depth to the water table.
Yep. The next one is, what is the hypothesis for decrease in N loss per unit of grain yield? As in, why might this be happening?
The hypothesis is that this is mostly driven by increases in the grain yield. So the denominator is increasing, and this drops down the scaled N loss.
Because actually your N loss is slightly increasing over time, I think 0.8% per year. Or yeah.
Okay. It was let me check this slide. It might be the signal there. I forgot to put a minus or a plus. Let me see that. 2 minutes. It was decreasing, so I need to reverse the slide.
So that's decreasing, but our N loss is slightly increasing, right? And
yeah,
yep.
That's correct.
The grain and export is increasing at a greater fraction. Yep.
Exactly.
Okay. Yep. Next one is, okay, for the water balance, what does the drainage metric represent? And I think you said that was either what comes out in the tile drainage or what moves kind of to deep seepage.
Yes, that's a great question, and I should have clarified this earlier. About 50% of Iowa soils, Matt, correct me if I'm wrong, has tile drainage. The other 50%, they don't have tile drainage. So for us to integrate the water loss as drainage, so in the soils with tiles, we consider this as a tile drainage. And also the water that goes below the tile line. And in the other soils without tile drainage, we consider as drainage everything that goes below the tiles to have a kind of a nice uniform summary there.
Next question is, it looks like your modeling of N loss was, and the summary was based on the annual precipitation. To what extent do seasonal variations in precip impact N loss?
Actually, there is, you can see the N loss to be 0 in 1 year and to be 100 in the other year. And I think in one of my slides, I mentioned that the coefficient of variation in the nitrogen loss was nearly 45, 50%. It's highly, highly variable. It's unbelievably variable.
Okay, the next one is, you showed that denitrification and N leaching were about equal and mentioned this as a water table effect. Would increasing drainage intensity reduce denitrification, and does your modeling effort give any insight into balancing increased drainage and leaching versus denitrification?
It's a pretty good, pretty good question. And this one, but through modeling, what we see as we increase drainage intensity, the flow, the direction of the nitrogen loss is changing. Once you relieve all the saturation from the soil profile, It's gonna change the story where the nitrogen is gonna go, to the atmosphere or to the tiles or further down. But in general, putting tiles, decreasing NTO emissions.
Okay. Okay, the next one is, how important have changes in temperature over the last few decades been in influencing grain yield and nitrogen loss?
That's another good question. Temperature is linked to many processes in the soil, including soil nitrogen mineralization, nitrification, denitrification, and also crop photosynthesis. Everything is driven by temperature. However, the delta change in temperature over the last 40 years, it's small. And compared to the interannual variability, it is even smaller. So it's not a big contributor of what we notice over the last 40 years in this simulation exercise.
Was a question here about finding greater soil moisture over time, but lower water table. I think by when you say lower water table, you mean shallower water table condition. Yeah, okay.
Thank you. Thank you for the clarification.
Yeah. Okay, and maybe kind of our last one here is, how do you think we could take this model and the findings to prioritize practice changes by farmers in Iowa to increase their environmental sustainability?
Excellent question. I believe lies the power of this model and many more models together and create a range of scenario options. We need to options so we have something to discuss and see and then select based on risk we are willing to take, not us, the farmers. And this also will help us understand trade-offs. We target something, but we improve this and we lose something else. So we need many scenarios to create so we can start thinking more about the future and have options to select and get these best options back to the experimentation.
Makes me think of one thing, because one of the things that I've heard you present a little bit on this before. So, there were some things that I had to relearn, but there was one thing that really caught me, which was looking at that, number of field days, suitable field days in the spring, and thinking about, the use of cover crops. And if they were to transpire a bit of water in the spring, is there any potential for those to maybe help with reducing early season soil moisture that might help us with increasing the number of field days suitable for work?
Yes, this is a potential solution. However, it is gonna be a function of the amount of cover crop biomass produced. The relation between water use, transpiration, and biomass is linear. So the more biomass you produce, the more water you are going to take out of the system. So I will leave it there.
Okay, well, and we found, I think, the more biomass we produce, the greater the nitrate concentration reduction as well in that leachate. So more reasons for a little more biomass. All right, with that, I think that got us through the questions. And thank you all for attending today, and definitely thank you, Sotirios, for another engaging talk, important talk. Really appreciate your willingness to share your information with the Iowa Learning Farms Conservation Webinar Series. So I'll give you the last word.
But it was, thanks again. I appreciate the invitation and all the discussion, and the questions were great.
Right.